Now, I would like to introduce my next speaker, Max. And, well, if you were here on the first day, he was giving also the workshop on Golang reverse engineering. That's going to be also related to his talk. And also, I would like, as he comes onto the stage, with an applause, he also got the first place in the chess tournament that happened on the 1st of October. With this, Max, welcome on the stage.
Okay, thank you for the kind words, and thank you for having me. So yes, as you just said, welcome to my talk about an introduction about reverse engineering Go malware. So about me, my name is Max Ufer. I'm a security researcher and malware analyst at the Fraunhofer FKE. I'm also a lecturer at the University of Bonn on binary analysis in general. And yes, I'm interested in anything low-level reverse engineering, binary analysis. So what are we going to talk about today? First, we're going to talk about a little bit about Go in general, then about Go in the current malware landscape, and then we will dive into the contents of Go binaries. So we will talk about the components of a Go binary, about the distinct language features, which are maybe different from other languages, and how we can analyze them easier. And then I will tell you about some useful tools and practical tips. So, I have to warn you now, this presentation starts with a jump scare. This is a nice little harmless Hello World program in Go with a sweet little gopher on the top. And this is what it looks like when you open it in your favorite disassembler. So you have many things which you maybe didn't expect. So you have some conditional jumps in the beginning. You have these scary-looking XMM registers. You have some abstract objects which are being referenced. Nothing that you would expect from a simple Hello World binary. But the goal of this talk is to take the fear away from you when you see something like this and show you that analyzing Go doesn't have to be that hard as it appears in the beginning. So about the Go programming language, a small introduction. It was created by Google in 2007 initially and was publicly released in 2012. The development was fueled by frustration over C++, which I think many people can relate to in the audience. Everyone who's I've talked to who developed something in C++ at least can relate in some way. Here's a direct quote. They wanted to improve programming productivity in an era of multi-core network machines and large code bases, and wanted to create a fast, statically typed, compiled language that feels like a dynamically typed, interpreted language. So basically, they tried to achieve a language which is as efficient as C, as usable as Python, but also memory safe, and offers this thing which is always referred to as effortless concurrency. So all these advantages have also attracted many malware authors. As you can see already in 2020 or 2021, there were many articles which were claiming this now is the year of Go malware. Now everyone's going to use Go. Obviously not everyone, but in my experience, it's getting more and more. A quick search on Malpedia already showed 50+ families which reference the Go language in the description of the malware. This is just the lower bound, as many families in Malpedia don't even have a description, so the real number is much higher. The main advantage for malware authors in Go, I think, is it's quite easy to write, but it's quote-unquote hard to analyze and hard to detect, at least right now. Another advantage is that it's cross-platform, so if you're, for example, developing your favorite DDoS botnet and you want to support multiple platforms, it's very easy in Go. You can just cross-compile it for every platform that you want to target, and you're good to go. And it has been used in many different domains, for example, in ransomware, the Hello Kitty ransomware, or the Night ransomware, which is now extinct because because now Ransom Hub has taken its place, which at least partly has been created on the same source code base of Knight, and now is one of the biggest ransomware threats currently active. It's been used in the DDoS domain, as I've said before. On the one hand, for example, the DDoSia project, which is like this volunteer network of people based or supporting the Russian Federation to carry out DDoS attacks against NATO-allied states. Zorgeka was another example that I've just analyzed recently, and it's also been used in other domains like rats, like the blue shell rat or the Zabroki rat, just to name a few recent examples. So, but let's dive right into the binaries. So I've just showed you the how the assembly of this small Hello World program looks like, and you've seen that it was relatively large for this simple Hello World functionality. And this also reflects in the size of the binary, but in an even bigger way than you might expect. So a simple Hello World binary, when created in C, is about 16 kilobytes big, at least on my machine. You can get it way lower if you try. But this simple Hello World program is already 1.7 megabytes large. And if you look at the symbols in this program, it contains more than 2,000 symbols already. And the reason for this is that Go binaries are completely self-contained. They have all these high-level features like garbage collection, concurrency, and these easy-to-use language features which try to make development more easier, but these are all contained in the binary, all the runtime stuff, not like other languages which are, for example, based on .NET. So all this stuff has to go somewhere. And this is one of the first issues that you will encounter when you try to analyze a Go binary. Because if you analyze a Go binary, for example, you just open it up in Gira and don't do anything, it will look like this. It's a little bit small here, but I think you can see there is like a whole load of functions on the left side. Also, the decompiled output is quite confusing. And yeah, this is still just a Hello World binary, but it contains more than 2,000 functions. And yeah, when you open this at the first time, maybe you don't even know where to start. So how can we tackle this? The main thing that we can use if we have just regular Go binaries is we can abuse one feature of Go, which I will present now. Consider this simple C program. You have an array, it has 10 elements, and then you try to access an element which is far off. What will happen? Segmentation fault. Now you have a similar thing, but in Go, like an array, and you try to access it out of bounds. Of course, you also get an error, but this error is much more verbose. It shows you the exact location in the source code where the error happened, and which function it was in, but also which source code file it was, what kind of error it was. So this means this information about the program has to be stored somewhere in the binary, so these stack traces can be created. And this is exactly what the program counter line table is for. So this is a graphic that I've taken from a very nice blog post from Google from 2022. And the program counter line table is a component which every Go binary in some sort has. The nice thing is also stripped binaries have this program counter line table because it's referred to by the runtime. In Alfa files, it's a dedicated section which is called Go PCLN tab. In macro files, it's also a section. In PE files, it's a little bit more difficult. It's referenced to by the symbol table, but even if the symbol table is not present, we can still find it because it starts with a magic, which is always, so some magic bytes. They are version dependent, but they are always there in this table. So what the tools that I will show you now later on will do, they will just scan the binary for this magic bytes, and then they will locate this procedure. No, I always have to say procedure line table, program counter line table. And what this table contains is, on the one hand, it contains the function boundaries of all functions. So it is used by the Go runtime to map virtual addresses back to these functions to create these nice stack traces. And it also contains all type information, which usually would be lost during compilation. So as I said, this table is always present in Go binaries. It can be corrupted if the binary is obfuscated, but we will talk about how to deal with this later a little bit. But in a regular Go binary, you will always have this table. We can abuse this to to recover all function names in a Go binary, even if it's stripped, which is very nice just because we have so many functions which we don't want to look at because they are just part of the runtime. There's also another structure which is displayed here, the module data structure. This also contains some nice meta information, like information about the Git repository the source code was in, and about the version and compile options. So this is also a nice little benefit. So this is just a short overview. If you want to know this in more detail, I would refer you to this blog post by Google. It goes into some more depth. So this is what a decompiler output looks like when you actually parse this structure. And the nice thing is, at least IDA does this by themselves. So this is not a sales pitch for IDA, but in my experience, IDA handles Go binaries, at least since version 8.2, quite well out of the gate. In other decompilers like in Ghidra, you have to deal with some plugins to do this, but IDA actually scans through the binary for this program counter line table, also when the symbol table has been stripped, and it creates this very nice output, which renames all the functions to the original names. It lists them on the left side in a folded structure, so you can have this package hierarchy restored. It also restores all the type information. And you can already see on the right side in the decompiled output that it looks way nicer. It almost looks like source code again. Yeah, and right now I've only told you about all the bad things that we have to deal with because of these many runtime functions which are part of a Go binary. But when we have recovered these names, it can actually make our jobs a lot easier. As Go is a high-level language, or a higher-level language, it deals with higher-level structures, and these structures are handled by runtime functions. So if we know which functions are the runtime functions and with which kind of objects they interact with, we can actually make use of this to quickly or more quickly understand what a function does without getting lost in all the details. So one example. You have this function here on the right. As you can see, it has already more than 500 lines, and we are not even at the end. There's much stuff going on. And if you would analyze this in detail just from this output, you would probably take some really long time. But if we just focus on the runtime calls which are being made here, which are nicely restored by IDA in this case, we can see this on the left. This is the function calls window, which just lists all function calls which are performed in this function. We can see that this function first makes many calls to some operations regarding slices, so like the Go equivalent of arrays, to put it simply. It converts some byte slices to strings, and then it calls the net HTTP new request with context function. So only from this, without looking at the code, you can already infer some functionality about the binary. So what probably can happen, and actually happens here, is you have some byte string which is being transformed in some way, converted to a string, and then an HTTP request is being created. So what you can now create as an hypothesis is maybe here is some string being decrypted, which is maybe related to some C2 functionality, and then an HTTP request is being created. And this is actually what's happening in this function. So if you now want to extract, for example, the C2 domains, of course you have to now go into more detail, but just by looking at these runtime functions, you now already have this overview which guides you in where to look to find this information that you're interested in this large binary, which takes multiple megabytes. So, when analyzing binaries, we usually have two ways how we can start. One way is to start at the entry point, to just get a broad overview what the binary does in general. So, how do we actually find the main function in a Go binary? Well, if we just have this regular binary, it's very easy. Just look for the main function, because the function names are restored, and you can just search for it, and then you open it, and then you're good. But what if you see something like this? This is an example of a program which was obfuscated with the open source obfuscator Garble. And one of the many things that it does is it corrupts the program line counter table. So we're not able anymore to recover the function names. So now you're again left in this situation where you have this big binary with many functions and you don't know where to start. There are two ways how we can deal with this situation. The one way is the Go compiler is a bit predictive in its behavior. One thing that it always does is it always puts the runtime functions at the start and the user functions at the end. So one easy way that you can do just to get to the user part is you just look at the functions which are at the bottom, and then you go through the cross references backwards. But this can, depending on the size of the binary, of course, take a very long time. So if you want to follow a more structured approach, we can look at this function here. This function is the runtime main function. It's the internal function of a Go binary which launches the main function. And it looks maybe a bit overwhelming at the start, but this is the end of the function. And this here, this is the call to the main function. So at least in the current version of Go, and in most of the samples, or all of the samples that I looked at, you will have this kind of structure in this function. So you have, especially what I always look for is this comparison at the bottom, the if with the two memory locations which are being checked, and then a call to a function which is not recognized by either. And this should be the main function then. This runtime main function is usually recognized by IDA as a library function due to their signatures, which is very nice. But you can also find it quite easily otherwise, if maybe something changes in the future and these signatures don't match anymore and you still need to find it. What you can do is you just look at the entry point of the binary, or the first function that is actually being executed, and then you go to the end of this function. And there you will see something like this. So you will see a few function calls, and before the third to last function call, an offset is being loaded. And it is actually passed to this, what is here called runtime bad mem call. And this offset here, this actually contains, after one more layer of indirection, the address of the runtime main function, so the thing you can see here on the right. And if you have found this, you can use this to find the runtime main function, and if you have this, you can use this to find the main function. So the other way, which we usually do things, is we don't start at the main function, but we look for this, what we always call cornerstones. So you look for these interesting things in the binary, like imports or, for example, strings, and then you go backwards from them and see in which context are they used. So let's start with strings. Strings are handled a bit differently in Go. So let's go back to our Hello World program. And if we run a tool like the Linux strings tool on it, we will see something like this. So we will see very large strings with seemingly no end. And yeah, this is a bit annoying because now we cannot directly see which strings are actually used in binaries and where they start and where they stop. And the reason for this is that they are represented differently than in, for example, C binaries. So this is how a basic C string looks like in a binary. So you have just ASCII characters, and then they are terminated by a 0 byte. This is how the same thing looks in Go. As most of you probably realize, this is not a string. It contains many 0 bytes, but it's actually a struct. And it starts with a pointer in the beginning, and then something which looks like a number. And this is actually how strings look like in Go. So you have like this struct definition where you have first a pointer to the data, and then a different variable which tells you the length of the string. And looking at the data, you will then there see the string, but without the 0 byte. So amazingly, we save 1 byte at the cost of 8 bytes, which tell us the length. It's really amazing. Yeah, so this is how strings are handled internally. Another thing which is important to understand when looking at these binaries is the calling convention. As you probably all know, calling conventions differ from different platforms and different programming languages, and Go is no exception for that, because Go created its own calling convention, and it also changed over time. So it used to be, before version 1.17, entirely stack-based. Now it's entirely register-based, except when it's not. So have a look at this simple Go program. At the bottom, you have the main function, and what it basically does is it reads some input and then calls a function and checks an error. And already there, you see a pattern which is very common for Go. Go allows functions to have multiple return values. And what you can see there at the bottom, especially when the vals function is being called, usual pattern is you have two return values for a function. One is like the actual return value, and the second one is an error. And then after you call a function, you check if the error is nil. If it is not, you have to handle the error. And if it is not nil, you have to handle the error. And if it is nil, you can proceed and use the return value. Let's see how this reflects in assembly. So this is like an excerpt of this program, how it looks like in assembly. So here's this call to the function which will first convert the arguments which are passed on the command line into an integer. As I already told before, in modern Go, since 1.17, we are now at 1.23, the calling convention is entirely register-based when possible. So this means arguments are passed in registers, and return values are also passed in registers, and they're actually passed in their same registers. So the first argument is passed in RAX, the second in RBX, the third in RCX, the fourth in RDX, and so on. And if you have multiple return values, you can also have more than two. It will be the same. So the first in RAX, the second in RBX, third in RCX, and so on. If you have too many values, for example, when you pass large structs, because struct fields, as we will see in a short time, are also passed as if they were separate arguments, then Go will switch back to a stack-based calling convention. So the motto here is either we have everything in registers or everything on the stack, but we never mix those two things. And there's an advantage to this calling convention, which we will see in a minute. So here, the stringconf a2i function, which you can see on the right, it actually gets two arguments here. So there's a memory reference loaded into RCX in the beginning. This is the memory location where the command line arguments are located. And then there are two values from certain offsets loaded into RAX and RBX. If you remember from the last slide, this is how Go handles strings. So in RAX, it loads the pointer to the raw string, and in RBX, it loads the length. And this struct is then passed to the a2i function. So as I just said, when we pass structs by value, internally it looks like the function gets multiple arguments, but it's actually one big struct. Then the vals function is called, but here only values are moved to EBX and ECX, and then the vals function is called. But we see we actually have three arguments which should be passed to vals. And this is like one small advantage of this kind of calling convention, that you have the return values and the arguments in the same registers. This just directly results in that you can chain function calls if the return value is the first argument of the same call. And this is something that you will see very regularly in Go binaries. So you can just have multiple calls, even especially if they only get one argument. You can just have multiple calls chained to each other, and it will look like on the first glance that they all don't get any input, but it's actually the return value of the previous function. So here we have, just as I said, the RAX value is like set implicitly because it is set by the previous function, and then it is passed to the next function, the vals function. And this thing at the bottom is just this structure which you will often see because it's this Go error handling. So you have like RBX, which is the second return value, which is being checked if it's null, and then depending on what happens, we continue in different parts of the binary. Let's have a look how this looks in the decompiler. So this is the decompiled output for the previous program. And this is the control flow graph of the assembly. So if you're attentive, you will notice two things. First of all, there's a branch at the beginning, which wasn't present in the binary. So it's, you can see my laser pointer now, but it's like this loop which is created here. This is a part of every Go function, because to enable this effortless concurrency, which we'll talk about in a second, Go functions have a very small stack, so they don't take up lots of memory. So at the beginning of each Go function, the program checks, do I have actually enough stack? And if we don't, we first handle this, we increase the stack, we get more memory, and then the function loops back to its beginning and starts to execute again. So this is the first thing which you will have in every Go function, which you can basically ignore most of the time. Then the second thing is, if we go back to the code, you would actually expect the branch at the end here after the vals call. But IDA doesn't display this here. So you just have the call to main vals, and then weird memory offsets are loaded, which is never a good sign in a decompiler, because it usually tells you that IDA didn't understand something correctly, and then one print line call. Yeah, and this is just a direct result. So this part is just a direct result because of IDA not correctly parsing or correctly interpreting the calling convention in this case. So IDA understands the Go calling convention, but here it just made a mistake. And we can very simply help IDA to display the right stuff by just creating a struct which represents this, these two return values. So in the pseudocode, we will have these multiple return values simply as structs. And here we just create a struct which on the one hand has this integer result, and on the other hand has an error. Error is actually a interface. How the type looks in detail, we won't talk about this here due to time constraints. But it's actually just also again a struct of 2 pointers, which you can create yourself, or if you have a Go binary which has not been obfuscated, as I said before, IDA recreates the types based on the program counter line table, and so you can simply use these types to retype the variables. And if you have a sample which has a corrupted program counter line table, you can, what I usually do is I open a second binary which has not been corrupted, and I just import the types from there over to my database, which has which is missing the types. Because the runtime types, if you manage to get the same version, they are the same. So you can just transfer them from a correct binary to a binary where the table has been corrupted. So if we apply this type, suddenly the code looks like this. So it gets way larger, and IDA now also understands where the branches are. So this is like a typical case which you often have when analyzing Go binaries, where the decompiler simply lies to you. So you really cannot rely on it only. You really have to look at the disassembly and help your tool of choice to understand what's really going on. But if you do this, then you can actually get quite a nice output, which is humanly readable, is maybe different, but it's closer to it. One thing when dealing with obfuscated binaries is that IDA, by default, tries to parse the Go version from the module info structure. And depending on the version used by the binary, it sets the calling convention. So if you have a version below 1.17, it sets it to the stack-based calling convention. If you have a binary which is above 1.17, you get the register-based calling convention. If you have a binary which has this meta information corrupted, IDA will default to the stack-based calling convention. But as I said, since at least 6 minor versions, this calling convention is not used anymore. So your functions will look like this on the right. It will still recover by using function signatures many of the function names, but all the functions seem to get no arguments. There's a simple fix for that. It's like a small tip for the IDA users here, is you can actually force the calling convention with the -o golang force rec.lb command. And if you do this, the same function suddenly looks like this. So these are just like these very small things that you sometimes need to help IDA with understanding, and then you will get a much more refined output. So let's get to one of the core features of Go, which is goroutines. I've already mentioned this effortless concurrency paradigm that they are following. So they introduced this Go keyword, which you can see on the left, which allows you to launch a function asynchronously. So you can call functions like just normally, and you can prepend the Go keyword, which will then launch them asynchronously, and you will get, for this example, some output like this, because these two functions seem to be running in parallel. Yeah, this is very easy to do, and the Go language by design encourages you to use these concurrent operations. So also in Go malware, you will very often see heavy use of goroutines. So we need to understand how this looks like when we see it in disassembly. So what you actually see here is, as often with Go, as it was also with strings, you will just have some more layers of indirection to the function calls. So when a Go function is, so a Go routine is called, you will see something like this on the right. So you will see a call to runtime new proc, which will get an offset passed to it. And behind this offset, you will have a wrapper function. If the function gets some more arguments, they will also be passed to this runtime new proc function, and will be part of one data structure. And this wrapper function then, this again then calls the actual function. So it will do some preparationary work, and then it will actually call the function that is being called. So it's not that hard to understand, but it's a bit annoying in a practical sense, because when you have this high-level look on a Go function or on a Go binary, then you do not directly see the calls to the functions that are being made there, because they are hidden between behind this one more layer of indirection. A feature which is very related to Go routines are channels. Channels are the mechanism of Go to communicate between different Go routines. So they are basically, yeah, channels. So they are a data structure where you can put stuff in and get stuff out. They are not like a queue in a sense that you can put multiple, like a buffer queue where you can put multiple parts of data in and then get everything first in, first out style out, but they are actually a blocking operation on both sides. And they can be used like this on the left. So they are created with the make keyword, which is also created to create different data structures. And then they can be passed to a Go routine as an argument. And then one routine can read from it, like you can see on the top, and the other routine can write to it. This is like a very easy kind of inter-process communication mechanism to communicate between Go routines, between different Go routines. So how does this look like in the decompiler? It's actually quite simple, because it basically directly translates. So at the beginning, we have a call to a runtime function, which is called runtime make chan. And it will get, as an argument, a structure which defines the type of the channel which should be created. If you have a binary which is not obfuscated, you will have it directly annotated. Then the Go routine is called. And this is this thing that I've told you about on the slide before. So here a new object is being created. So this, before we saw the disassembly view, this now is the decompiler view. A new object is being created, and there's first this main GoWrap function, which is being written to it, and then on the low end, you will have this v2, which is written to a different offset of this object. So this and this object is then passed to the runtime new proc function, which actually launches the Go routine. So it passes the reference to the wrapper function, which will then actually call the Go routine and the argument to it. And here's also something that you will very regularly see when you look at Go binaries in the decompiler. You have these very many variable reassignments. So this v2 variable, it is assigned to the channel actually, but in two different places, because this big branch which is happening here, it's like some runtime garbage collection stuff which is happening, and depending on some internal runtime workings, it would just operate in a different way. But the gist that I want to tell you with is that you very often have the case that you have like objects being created at the top, then they are passed around variables created by your decompiler, like a whole lot, and then finally they land somewhere, and it can be quite confusing to follow this data flow. So here the best thing that you can do is that you look at the function calls that interest you and then just go back and traverse all these assignments until you reach the point where they are actually being created or assigned. So here this, as I said, the goroutine is being called. And then a message from the channel is trying to be received. And this is done with also with a simple runtime function, the runtime channel receive function. It just gets two arguments. On the one hand, it gets a reference to the channel, and then a memory address where the resulting value should be placed. And then at the end, channels need to be closed, so you also have a call to this runtime close channel function. And if we look at the channel function, it's actually quite simple. It gets as an argument the channel, so you can also clean it up a little bit, and yeah, you just use the equivalent of the runtime channel receive function, the runtime channel send function to write stuff to the channel. So yeah, a thing that I wanted to mention, because it looks very similar to goroutines in the decompiler, is the defer statement. Defer is a statement also introduced by Go, which basically tells the program, hey, perform this function call at the end of my function. So you literally defer it to the end of the block. So this program, which we have here, which just calls print line with a defer keyword 10 times, it internally creates a stack where all of these function calls are placed, and then at the end they are handled like in reverse because it's a stack. So the output of this would be like the reverse counting from 0 to 9. Of course, this program doesn't make much sense, but what defer is usually used for is for doing cleanup work at the end of the function, so you don't have to remember to do this at the end of every error case. For example, if you have to close a channel at the end of a function, you can create it, and then you can defer the closing of the channel, and you don't have to think about it again. And how this looks like in the decompiler is actually very similar to how goroutines are handled by the runtime. So you have an object which is being created with a wrapper function again. Now here it is called defer wrap. Before it was called go-wrap. And then you have a function called runtime defer proc. And this will basically put this function call on the defer stack. So it's basically, the structure is the same as it was for goroutines. And then at the end of a function, there will be a call to runtime defer return. And this function will then handle this stack of function calls which has been placed during the function, and will call all the functions in reverse order to perform these cleanup operations. This defer thing can also be inlined by the compiler. So if you only defer one function and there are not many conditionals, then usually the compiler will inline these calls. But from a perspective of reverse engineering, this doesn't matter that much for us, because then we actually just see the function calls and don't have to have this layer of indirection, and we don't have to go through these defer wrap functions. Okay, then there's one thing that I also want to show you. Here we have a, it's a peculiarity of Go programs. Here we have a simple program which just creates two arrays. One is initialized with some values, one is initialized by as 0 by default, and then we just have a function which prints this. And if we look at this in IDA, it looks like this. So first of all, there are many casts. This is also a regular thing when dealing with Go binaries. So I usually, first thing I do is just turn off all the casts, so you don't have to have an ultra-wide screen to see everything. But then, as you can see here, we have calls to memory locations. So these are not locations which are identified as functions by IDA, but they are just locations in the program. And if we look at this, we see something like this. So a very, very long function, which is just like a linear set of instructions. And if we look at the disassembly, we can actually see that it's a repeating pattern. So we have some pointer in RDI, and then you always have this repeating pattern of 5 instructions. So the value at the pointer and at the next offsets is set to the contents of this XMM15 register, and then the pointer at RDI is increased. And then the whole stuff repeats until the function finally returns. And this is actually an optimization used by Go to zero out buffers of different sizes. So XMM15 is actually a special purpose register in Go, and you will see it regularly all across the place. And it is just always a 0. So this is the register Go uses when it needs a 0, and it can be used to zero out other memory locations. And the purpose of this very long function, and the reason why we see calls to these memory locations, is that this is first of all, it's an unrolled loop. So you could also do this in a loop, but the advantage of doing it like this is that you can use it to zero out buffers of different sizes, because you can simply jump to, or you can call into the function at different offsets, and then depending on where you start, it will zero out a buffer of a different size. This is actually like a quite nice little optimization, but it results in this, that you have these calls to some weird-looking locations. But if you see this in Go binary, it's usually one of two things. It's either this, so it's a zeroing mechanism, or the equivalent. Yes, this is the registers. The equivalent is the DAF copy function. So the previous one was called DAF0, named after a programmer who worked at Lucasfilms, who was tasked with optimizing these kinds of operations. And here's like an equivalent function which is called DAF copy. And as the name says, it basically does the same thing, but not for zeroing out memory, but for copying buffers. So it is also this unrolled loop structure, which will help you, or help the compiler to efficiently copy one buffer to another thing. This is, you will regularly see this when arrays or large data structures are either initialized or passed by value to functions. Yes, so we're nearing the end of my talk. Just some useful tools that you can use in practice. The most useful tool of everything, as usual, is the official Go reference. So the easiest thing that you can do if you have something in your binary that you don't understand is try to recreate it. Write a small program which does this one thing that you don't understand, like you have a crypto function which is being used and you don't know where the key comes from. Write a small program which implements the same crypto function, compile it, preferably on Linux with debugging symbols, and look at it in IDA. Because if you provide IDA with debugging symbols, you will actually get quite a nice output, and it will help you correlate what's actually happening in the program. Another small tool that I like to use just for a quick first look is redress. It's a small tool written in Go which parses this PCL-NTAP structure and can give you some information about it. It also has some integration for a radar array if you're like a user of that. And it can give you like this small overview about how many functions are in the binary, which compiler configuration was used, and a thing that I like to have a short look at sometimes is it can give you a source code projection. So it will show you all the source code files and how many lines they had, and you can get like a quick insight in how this binary that you looked at was structured when it was programmed. It is built on a library called Gore for Go reverse engineering. It's like a nice, small Go library if you want to write your own tools, which provides you with some nice functionalities in regarding to parsing this PCL-NTAP structure. Another thing which is like doing the same but more is Gorism. It was created by Google, and it basically does the same thing as redress, but way more. It also comes with plugins for multiple different disassemblers, I think at least for IDA, Ghidra, and Binary Ninja. And it's basically tries to fill these gaps that some of these tools have when it comes regarding to parsing Go binaries. Another thing that I've found quite useful in the past is CERT.LV. CERT.LV is like a semi-official Go debugger, which is not directly targeted at reverse engineers, but more for developers. But it also parses all these Go structures. So what you can do is you can use, for example, the funcs command, and you will directly in your debugger have all these all these functions in from your malware that you're looking at, and you can set breakpoints on it. In practice, it feels a bit like GDB, but worse, because it handles a bit like GDB, but it's missing many features. But especially on Linux, when you just want to do some quick binary analysis, get some values out of some registers, I think it's a nice thing to do because you don't have to like calculate around with memory addresses if you have a binary where the PCN tab is intact, and can get just some quick results. And one other thing, also some kind of advertisement, a colleague of ours, Daniel Ploman, which many of you probably know as the Malpedia guy, created this tool called mcrit. It's a binary analysis framework which you can use to compare binaries on a basic block and function level. And one thing which it was not created for, but what you can do is when you have binaries which have malformed PCL tab structures, is you can load as many Go binaries as you can build from different versions into it, and then use, for example, the IDA plugin to correlate the internal runtime functions to the functions that you have in your created benign binaries. So you can use it actually to rebuild the symbols in your binary of the runtime functions, even if the PCN tab structure, for example, has been corrupted. So that's it from me. Thank you for listening. Thank you for having me, and have a great rest of the day.
All right, thank you. Before that, with the applause to the presenter, I would like to open up the questions. Also, we can take one or two questions from the audience. Is there anyone who wants to ask a question from the audience? Okay, I will kick off. At least I will ask one question from myself, and there is also one question that's been sent in remotely. Now, you mentioned that the Go compiler has been moving now to kind of put all the variables into the registers. To my best knowledge, I know that the GCC also uses on 64 bits, also the registers to store all the variables. That minimizes the stack usage. Now, coming down to this, you said minimal use of the stack. However, still the backtraces will be available through the stack so that we can see the call chain, or that is stored somewhere else. How would the stack minimal use would be implemented? Does it rely on other structures, like heap, outsourcing somewhere else?
So I'm actually not sure if I can answer the question. I mean, the arguments are passed around in the registers, but I'm quite sure. I cannot say it at 100% certainty, but I'm quite sure that return values are still placed on the stack, so it allows recreating these stack frames, as well as local variables are also placed on the stack. So there are still some function frames on the stack which are present. It's just the arguments which are, if possible, passed on the registers.
All right, I will take the question one from the menti.com. The question is about the obfuscation of the Go binaries, and there's a specific tool that the question author asks, Garble. I'm not sure if you're familiar with it. Yeah, you are. And the question is, like obfuscation of Go binaries, will it be flagged by the antivirus?
Yes.
Yeah.
So when I created the workshop, I created some reverse engineering tasks for the participants, and I created a very small benign binary which was just like the simplest of crack me's that you can think of, and I just obfuscated it with Garble, and Windows Defender kept removing it from my system. So even though I wasn't dealing even with malware, I had to disable the Defender on my system or on the system for the workshop participants, just to enable them to have a look at these obfuscated binaries, because as of now, Windows Defender seems to be very strict about this. So they just don't even care if you have actual malware or not. They will just kick it off your system.
Before you depart, do you see the tendency to increase in the Go malware? Is it more dominant? Is the Go the dominant malware language, or you still see that other languages are still there?
Well, I think C is still the main language, and it will also remain that way. But in my personal experience, it's increasing, because it's easy to write and it's cross-platform and you get this many nice features. Garble is also, like, from a malware writer's point of view, a very nice obfuscator, because it's super easy to use. You just, instead of Go build, you write Garble build, and you have an obfuscated binary. It can introduce these nice things like control flow flattening, and it will obfuscate all your strings, corrupt all these control structures. So it's like a very low effort, high reward thing. But I don't think it will overtake C, but I see it increasing. Yeah.
All right. You have absolutely deserved the candy and the socks. So thank you for the talk. Let's give a round of applause.
Thanks. Thank you.